Hi everyone. Today we will continue our discussions on the practical transformer. So in the last session we stopped on this slide here. So here we will discuss today or start from the parameters identification of equivalent circuit or an identification of equivalent circuit parameters of the practical transformer. So firstly, why it's important to make parameters identification? This is in general, not only for the transformer topic. So for any device, guys, we need to evaluate this device. So we mentioned before, in order to make any evaluation for a circuit or for a device, we have to make equivalent circuit firstly. So we made the equivalent circuit now. Second step is we need to know the efficiency, for instance, of this device. In order to know the efficiency, I need to know the parameters. For instance, I have here some resistors, R1, R2 prime. So these resistors here, guys, will consume some power loss. So how can I get the efficiency without knowing these parameters? So it's not possible. So in order to evaluate the efficiency, for instance, of a device, we have to have the resistors here. Also, in order to know, for instance, the voltage regulation depends on the difference between the input and output volt of the transformer. So we have to know all the parameters of the transformers here in order to know that. So generally, guys, in order to make any kind of evaluation for a device, you have to have the parameters. For that, parameters identification is very important. Another thing is in control. So for motors, for instance, or generators, in order to make control for these devices, you have to know all the parameters of these devices. So control as well require the identification of these parameters. For that, for any device, we should make equivalent circuit and identify the parameters. So the parameter identification of the transformer is very simple. We will discuss it together, how to make the identification and obtain all the transformer parameters. In order to do that, for a single phase transformer, and we can do the same to three phase, so we need to make two different tests. One test is called open circuit, and the other test is called short circuit. In other devices or machines, which works as motor, we make what's called no load, which is the same meaning of open circuit here for the transformer or in generator as well. And we have another test called blocked rotor, which is also equivalent to the short circuit. So these are the well-known tests we use for electrical machines in order to identify the parameters. Let's start see the open circuit. How can we make this test and what is the equivalent circuit in case of open circuit, for instance? So here in the left-hand side, guys, you can find this is the equivalent circuit in case of no load. So no load means this is a practical circuit we have. This is the first approximation we made. So we move the parameters to the load side, not the source side. But still all the circuit is referred to the primary side. So here, guys, if I made no load or open circuit, so this means I2 prime equals 0, which means all the voltage drop across this impedance here would be 0. So we can say the volt at this point now is the same as V2 prime because the voltage drop here is zero. So this is going to be now the equivalent circuit in case of open circuit or no load. So we simplify the circuit of no load to be like this one. I'm going to say later on how can we make the test, but let's understand firstly the effect of these tests on the circuit or getting the equivalent circuit of these tests. What about the short circuit? Let me firstly erase this part here and see together, guys, what will happen if we have a short circuit. So short circuit test means shorting the load terminals. If I'm shorting the load terminals, assume that I have a transformer of 2200 to 220 volt. Assume this is low voltage, sorry, a step down transformer. So for this transformer, the secondary is 220 volt, which means the secondary volt referred to primary side is 2200. So V2 prime is 2200. Can you imagine how much current we would have if you make short circuit on a 2200 volt? It's very huge volt. Sorry, very huge current because the volt is very high. So in this test, guys, firstly, we will not make a short circuit at the rated volt. So I'll discuss with you the procedure of the test, but just here, let's understand the concept in order to provide the circuit. So we will not apply the complete volt. However, I will apply a volt to guarantee the current flow here is going to be rated current. Rated current. Rated current can be obtained from the nameplate data of the transformer. So for any device, guys, we have what's called nameplate data. So the nameplate data, I'll show you some nameplate data examples today. So the nameplate data means all full load or rated values of this device. So we will see one nameplate data for a transformer soon. So here, if this current is rated, we discussed before, guys, that the current flow here is relatively small. It's around 5% at most. So in this case, if we neglected the current flow in this branch, the circuit would be only this series circuit. So this now can be the short circuit test equivalent circuit. Okay, so this is the meaning of making this test, guys. So firstly, we make the test in order to simplify the circuit, or this is the target of this test. So in this test, as you can see here, we have just RC1, which is the core resistance, and XM1, the magnetizing reactance in this circuit. So if you have a certain volt here and you know the current, so it's going to be very easy to get these two parameters. And here as well, if you have the voltage magnitude and current magnitude, so it's very easy to get the values of R and X. So this is the concept. Once you got these parameters, you can write down these parameters here, and by this, you already made the parameters identification of the transformer. Now the question is, how can we make these tests? So let's firstly describe how can we make these tests, guys. For the open circuit test, or let me, guys, write one more slide here. So for the open circuit test, so here, this is our transformer. we connect the transformer to a single phase supply, ammeter, and wattmeter. So we will measure the power, the current, and the volt through the voltmeter here. So I'm gonna call this is V open circuit, P open circuit, and I open circuit. So we will do that on the primary side. We will make the measurements on the primary side and having the secondary side open circuit. So the meters are connected to the transformer as shown beside. It is preferred to connect the meters and supply at the low voltage side. So we do prefer to have the volt and supply at the low voltage side. At rated volt, so we should increase these volt guys until having V rated, and the rated value could be obtained from the data from the nameplate data of the transformer. So at rated volt, measure the supply current and power. So we will change the volt until having the supply volt equals V rated of our transformer. Then we will observe the current, power, and voltage magnitudes and record these values. For sure, the voltage magnitude has to be the same as V rated. So we will make this test at rated value all of the time. And there is a reason why we make it at rated. We make it at rated because we need to calculate the core resistance at rated supply, because all of the time we will consider the core loss as constant value, whatever the loading condition, and it has to be calculated at the rated supply volt. So this is a condition all of the time, guys. Rated volt has to be applied to the transformer in open circuit test. And we can refer to the open circuit loss as core loss. So I'm going to write this down here. Open circuit loss equals core loss. Because, as you could see in the open circuit equivalent circuit, we don't have any other resistance, just the core resistance. So this means any power consumed by this circuit would go to the to the core loss of the transformer. So the open circuit loss is nothing but the core loss. For the short circuit test, since we mentioned, guys, the short circuit current is high, so we shouldn't apply the rated volt. We should just have the rated current. So this is the procedure here, how to make this test. So the meters are connected to the transformer as shown here. So we have also power, or we will measure power. I'm going to call it power short circuit, I short circuit, and V short circuit. It is preferred to connect the meters at the supply at low voltage side, and at rated current meter supply voltage and power. So we measure at rated current. So by the end, I short circuit would be I rated, P short circuit, and V short circuit will be measured. Short circuit volt, by experience, it's going to be less than 10% of the rated volt. Okay, guys? So this is the open circuit and short circuit test. After doing that, you can have the parameters, or you can have the values in order to calculate the parameters. Here is an example, guys. How can we use the values of the test in order to calculate the parameters? So in this example here, guys, we have these parameters. So tests are performed on a single phase 10 kVA 2200 220 60 hertz transformer. All of these data, guys, we refer to these data as the rated values. So these are the rated values, and these are obtained from the name plate data. Let me show you now quickly, just on Google, what is the nameplate data looks like. So this image here is clear. I'm gonna copy this image and keep it here in our slides. Just a moment, guys. Okay. So here, this is a transformer made by a company called ABB. So ABB is one of the well-known companies. So we have companies, guys, that produce a lot of electrical equipment. One of them is ABB. You have others like GE, like Eaton. So all of these are very well-known companies here in the United States and worldwide. So ABB is one of them. And I'm going to say something regarding the values we have here and refer to one important thing also you need to know. So, for instance, here, this is a type. So this is a certain type of transformer. Okay, it's something related to internal to the company. This is the year of manufacturing. Number of phases is 3. Number, so this number also is like a serial number related to the company production. Here, rated power. So rated power is 100 kVA. So 100 kVA is the apparent power of this transformer. Transformer 2 specifications, EN/IEC. So this is a standard of transformer, but this is IEC standard, which means it's European standard. It's not American standard. Okay, so you can find American standard as well as NEMA standard. So this is not the American standard. For that, you will have some differences here. You will see that with me right now. So here, guys, you have rated volt and rated current here. Can you see, for instance, this is the high voltage side data, and this is the low voltage side data. So for the high voltage side data, we have 11 kilovolts, plus or minus 2 times 2.5%. So this is like available, like clearance or difference in the windings voltages. So it's possible to be more or less by 2 times 2.5%. So it's up to plus or minus 5%. The low voltage side is 415 volts. So this is actually medium volt transformer, and the 415 volt is the line to line volt in Europe. So this is equivalent to the 240 volt for domestic loads here, or 480 volt in industrial three-phase load. So this is the low voltage level of this transformer. Now, the current is 5.25 amperes, so this is the high voltage side current, and the low voltage side current is 139 ampere. So these are the rated values, guys, rated values of currents. Okay. Then this transformer has something called tape. So what is the tape? So tape is used for variable voltages. So we have tape moved on the windings to have different voltage values. We will discuss this by the end of the topics of our transformer actually. Okay. So we have tapes here with different voltage values as you can see here. Also you have here some information about the connection symbol, about the cooling system, ONAN or ONAN. So we will discuss also what the meaning of cooling of transformer. Rated frequency is 50 hertz. This is what I refer to, guys. So this is IAC standard. It's not American standard. For the American standard, you know that frequency is 60 hertz. Short circuit impedance is 3.88. This is something related to the protection, guys. It's not related to the short circuit test of our work, but this is something called short circuit impedance used in case of transformer operation during fault analysis. We have what's called load losses. We have no load losses. So load losses, guys, is referred to copper loss. And no load losses is referred to core loss. So the core loss is 145 watts and the copper loss is 1750 watts. Then you have something related to the total mass, mass of active parts, and so on. So these some are mechanical parameters. So we are focusing only on electrical parameters today. So we got some parameters that we can use in our example. So if we go again now to our example, guys, we'll find that these data are given already from the data sheet. Here we have single phase, not three phase transformer, 10 kVA, so the kVA should be written also in nameplate data, 220 or 2200, 220 volts, so this is the primary and the secondary voltage levels, 60 hertz. So the current is not given right now in the example here. So also he referred to that he made the open circuit and short circuit test, and here are the results. So what results we have right now here? We have the open circuit test and we have the short circuit test data. So the open circuit test data, and he referred to here, he made the high voltage side open. High voltage side open, so this means the devices of measurements are on the low voltage side. So we all of the time, guys, we measure from a side and make the test on the other side. So this means in this example, we will have measurements on the secondary side for this test. So this means all values here are referred to secondary side. What are these values? Volt and current. Power has no side. So power is power whatever the side. However, this current and this volt are referred to the secondary side. And for the short circuit test, we have this is V short circuit, I short circuit, and P short circuit. And he mentioned here, guys, low voltage side is shorted. So this means the measurements are installed on the high voltage side. High voltage side is the primary side. So all of these readings here are referred to primary side. So you have to figure this out during the test. Otherwise, all the numbers will be incorrect. So open circuit test data are referred to secondary, and primary and short circuit test data are referred to data is referred to the primary side. Now, let's see, guys, how can we get the parameters. First thing here, guys, is drive the parameters for the approximate equivalent circuit, refer to the low voltage side and the high voltage side. So he needs to calculate the parameters in both sides just to train you on how to do the calculations on both of sides. But practically, for sure, one side is enough. Then part B, express the excitation current as a percentage of the rated current. Excitation current is the no load current. So here he just need to make you sure about how per unit is the excitation current. So we mentioned that excitation current is around 5% of the rated current. So we will see how much we have here. Then determine the power factor for the no load and short circuit test. This is just to give you the sense of how much power factor we should see during open circuit or short circuit. So preliminary now, guys, we need to know the parameters. So in order to do that, let's write down our given data here. So for this transformer, guys, V high, which is the primary volt, is 2200. V low is 220 volts. I high side, if I would like to calculate the I at the high side now, so I can say S rated divide V. So S rated is 10 kVA, so 10,000 divide 2200. So the current is 4.55 ampere. So this is the rated current referred to the high voltage side. So here, guys, instead of mentioning 1 and 2 as primary and secondary, he referred to the sides by means of high and low. So high is the high voltage side, which is the primary side, and low is the low voltage side, which is the secondary side here in this example. For the I low rated value, if you would calculate this to the low voltage side, so 10,000 divided 220, so it's going to be 45.5 ampere. If you compare these values we have here to the test data, you will find that firstly, the open circuit test is made at rated volts, and this is the condition we mentioned. We have to make the open circuit test at rated value of volts. And as we mentioned here, this is referred to secondary, which is low voltage side. So you know that the low voltage is 220. This is one thing. The other thing is for the short circuit test, the current short circuit is rated current of the transformer. So this is the high voltage side. If you go to the I high voltage rated here, so it's 4.55. So the test has to be made at rated current. So you have to be sure about these 2 points. Now let's drive the parameters together. So starting firstly, guys, with the no load test. So this is the equivalent circuit of the no load test. Now, guys, I have V, I have I, and I have power as well. I'd like to start with the easiest part, which is, you know that power, guys, is consumed all of the time on resistors. So now you have resistor. You know that power, in general, guys, this is generally power. It could be I square R, or it could be V square divided R. This is generally the power across a resistor. But this is only if you have resistor like that, and you know the current flow and the voltage around this resistor. If you have a look here, guys, do we have the current flow in this resistor? Actually, no. The open circuit current we have is I1. We don't have IC1. However, we have V1, which is the applied volt across RC. So we cannot say P equal I square R here because we don't have the current. But we can use the voltage V1, which is the open circuit volt, because this is the applied volt across the resistor in order to get the power across this resistor. So we can say now, guys, since power is already measured, so we can say P open circuit equals V L square divided RCL. L is low, Okay, so VL is low voltage side, square divide RCL. So we will calculate the parameters to the low voltage side. Power is given, voltage is given, so the unknown here is RCL. So RCL equals V square divide P. So V square is 220 volts square divide power equals 100 watts. So we can get the poor resistance referred to the low voltage side, which is secondary side here in this case. Then, after getting this resistor here, guys, we still need to calculate this reactance. How can we do that calculation? Here in this example, the textbook firstly calculated the ICL. So since you have the resistance now, you can calculate this current. So we can say V divided R equals IC. So he calculated the IC here, 220 divided 484, so it's 0.45 ampere. Then, if you have current flowing in a resistor and reactor in parallel like that, simply you can say this current here, guys, equals square root of real square plus imaginary square. So he calculated IML, the current flowing in this reactance, as IL square, which is the no load current. This is the IL, the given current, minus ICL square under root 2. So this is now the current. So 2.5 square, this is a given open circuit current, minus 0.45 square under square root of 2. So this would be the current flowing here in this magnetization reactance. So now we can say the magnetization reactance equals V divide I. So 220 divide 2.46, it's 89.4 ohms. This is a way. You can make another way, guys. So I'm gonna write here another solution, and whatever solution is good for you, you can use. So you can calculate the power factor of this current. So power factor equals cosine inverse P divide VI. After getting this power factor, you would have the angle of this current. So then we can say theta IL equals power factor is not cosine inverse, this is the angle. So power factor equals P divided VI. Then theta I equals cosine inverse of this power factor. So we got now the angle of this current. We got the angle of this current. So the power factor equals P divided VI, and theta IL is cosine inverse of this power factor. So if you got the angle of this current, so now you can say IC, which is ICL, equals IL times cosine theta IL, and IML equals IL times sine theta IL. So this would give you the poor resistor current, and this is the magnetization reactance current. Once you have these two currents, you can say RCL equals VL divided ICL, and XCL is VL divided IML. So this is another way, guys. Whatever the technique you like, you can use. Okay, nice. Here in this example, guys, he asked to calculate the parameters referred to to both of the sides, to the low voltage and high voltage side. So this side here is the low voltage side. So we got now RCL and XML. We need to have RC high and XM high. So in order to do that, we need to refer the parameters from the low voltage side to the high voltage side. Again, this transformer is 2200 220. So this is the high, this is the low. So this means our turns ratio is firstly equals 10. Now you calculated the parameters referred to the low voltage side and you need to move to the high voltage side. So respect the value of the turns ratio. So we would multiply times A square. So for that, RC high equals A square times RCL. So 10 square times 484. So this is 48.4 kilo ohms. Regularly, guys, the core resistance in the high voltage side is going to be very huge value like that, because by the end, the current is very small in the high voltage side. And similarly, the value of magnetization reactance, XM high, is A squared times the XM low. So this is going to be 8.9 kilo ohms. Okay. So here we got the parameters of the magnetization and core branch and the no load test. We still need to continue calculating the remaining parameters, the series parameters of the circuit, and this will be from the short circuit data. So let's move to the short circuit test. Let me draw the short circuit test equivalent circuit right here. So this is R equivalent, this is X equivalent, and this is the short circuit. So we have here V short circuit, we have here the calculated I short circuit, and this is R equivalent, this is XL equivalent, and here this is our short circuit. Firstly, this test is made while measurements are connected to the high voltage side. So all parameters we will get here are going to be at the high side. Now, this is a series RL circuit. So we can say simply now, I squared times R equals P. So since power short circuit equals now I short circuit square times R equivalent high, so we can say R equivalent high equals P short circuit divided I short circuit squared. So here is the substitution, 215 divided 4.55 ampere square. So the value of R equivalent to the high voltage side is 10.4 ohms. Now, we need to calculate the imaginary part of the impedance. So let's get firstly the impedance value. We have the real part, so we can get the imaginary part. So we can say Z equivalent, guys, here equals V high divided I high, 150 volt divided 4.55 ampere. So the current here, sorry, the impedance here equals 32.97 ohms. Now, in order to get the imaginary part of the impedance, you know, any impedance, guys, let's say Z equivalent high equals R equivalent high plus J X equivalent high. So you need to get the imaginary part. You can use the triangle equation now and make X equals root Z square minus R square. So we can get simply the value of X equivalent. After getting these parameters, you know that we made this test while devices are connected to the high voltage side. So we need now to get the low voltage side. So we need to divide over the turns ratio square. So we can say R equivalent low equals R equivalent high divide A square. So this would be the resistance referred to the low voltage side, and this is the reactance referred to the low voltage side. One more thing, guys. sometimes we may need to know every winding, which means this is R equivalent, which means R1 plus R2 prime. I can say here, so high voltage side is the primary side. So I can say that R H plus R L prime, these summations equals R equivalent high. Correct? And I know now the total R equivalent high. If I would like to get separate values for every resistor, the equivalent series resistor of the winding, so I can say or assume that R high equals R low prime equals R equivalent high divided 2. So this assumption is acceptable. And in this case, R high will be 5.2 ohms and R low prime will be 5.2 ohms, which means R low prime, you can get it from the other side. R low equals this value divide 2, which is going to be 0.052. So this is the real value of the equivalent series resistance of the low voltage side windings, and this is the exact value of the high voltage side resistance of the windings. Okay, nice. So by this, we could calculate all the parameters of our transformer. This is part A. By the end, guys, just to simplify, you should draw the equivalent circuits of both high voltage side and low voltage side, refer the equivalent circuit, and both all the parameters on the circuit, as you can see. Part B, express the excitation current as a percentage of the rated current. So you know that the no load current here, guys, is the excitation current. So we have here no load current of 2.5 ampere. And this is referred to the low voltage side. And the rated current referred to the low voltage side is 45.5 ampere. So what we can do is just divide 2.5 over the 45.5 and get the value. So 2.5 divide 45.5 and in percent, so this would be around 5.5%, which is making sense. The other thing is calculating the power factor at no load and short circuits. If you calculate the power factor is nothing but P divided VI. So this is the no load data, P divided VI, and we have here 0.182, and also the power factor during short circuit test. By this way, it's gonna be 0.315. As you can see, guys, all of the time power factors during open circuit or short circuit tests are gonna be very small values. So it's not representing any kind of loading of our transformer. Okay. So to this point, guys, we covered today how to identify the transformer parameters. The same for the three-phase transformer will be used just with very minor modifications in the power relations, because the power relations, you know, in case of three-phase, guys, for three-phase, you know that any power, any active power equals √3 V line I line power factor, or 3 V phase I phase power factor. So in this case, if you replace all of the relations here with the power relations, so as you can see here, guys, we use the power relations to make calculations. So here, for instance, for the no load test, we use the power here, correct? So instead of that, VL should be considered, is it line or phase volt? And the value is it 3 or root 3, and consider this in all of our calculations. So this is the only difference between single phase and three phase transformer. Okay. And you would find that also in any other calculations in terms of is it V line or V phase. And all of the time, guys, we, for the parameters, we care about the phase value, because any parameter or any impedance by the end equals V phase divide I phase. Okay. So this is the only difference between parameters identification of three phase and single phase. We will care of getting the exact or the correct voltage and current representation in the calculation. Okay. And so we can now make any kind of parameters identification for open circuit, for single phase or for three phase transformer. Next class, guys, we will start from this point, which is the voltage regulation. Thank you so much.